Hi everyone, welcome to moscan.com. So in today's video, we have been given one question which is based on an ideal op-amp. So you can see one circuit is drawn here. So if you know the basic standard architecture of op-amp, you must be knowing कि one op-amp, if it is given like this, and at the negative terminal, if this kind of structure is applied, so this is known as inverting configuration of op-amp. And for this inverting configuration of op-amp, if I have to write the transfer function, I can write as V naught upon V input in Laplace domain would be equal to minus RF upon Rin. RF is basically feedback resistance and Rin is input resistance which is applied here. So similar kind of structure is given in this question also. It is given in question कि we can assume the op-amp as an ideal and we need to find out the transfer function. So these kind of questions are quite common in GATE exams and even in your undergraduation exams also. So some RLC kind of structure is added in feedback also and in input path also, and we need to find out the transfer function. So let's start solving this question. So while solving this question, we can assume, we can divide in two parts. Like the standard architecture, I can assume this as input part. For this we will calculate the impedance, and this entire structure I can consider as feedback part. And for this also, I will calculate the impedance, and then we will do minus Rf upon Rin, and we will get the transfer function. So if I start solving from input part, so Z of input I can write as these two are in series, so we need to add the impedance of this resistance plus impedance of this cap. So impedance for resistance can be directly written as whatever we are getting here, so that would be equal to 200 ohms only. Whereas for cap, we can write in terms of 1 upon SC. C is 1 millifemto is given, so basically 10 to power minus 3. So if I solve it further, I will get LCM as S into 10 to power minus 3, whereas if I multiply this with 200, I will get 0.2 S plus 1. So this is Z in which I have calculated, and it is the series combination of resistance and capacitance. Now for feedback, if you see, so we need to first calculate the parallel impedance of resistance and cap, and that value will be in series with this inductance. So we know if we have to replace this inductor in Laplace domain, it will be replaced, L will be replaced with SL, R will be R, and cap will be replaced with 1 upon SC. So that's what we have done here. Cap is replaced with 1 upon SC, resistance is same, inductance will be replaced with SL. So if I have to calculate now feedback resistance, so first let's calculate for this part. So here R and C are in parallel. So parallel, I can write the equation as ZR into ZC upon ZR plus ZC. ZR I'm assuming is 200 and ZC is impedance of this 1 millifemto cap. So if I further solve this, ZR is 200, ZC would be equal to 1 upon SC, S would be S, and C would become 10 to power minus 3 divided by 200 plus 1 upon S to the power S into 10 to the power minus 3. If I solve it further, I will get 200, because once we will take the LCM, this S into 10 to the power minus 3 will get cancelled out from numerator and denominator, so I will get 200 divided by 0.2 S plus 1. This is what we will get. So this is not the final ZF, I can call it as ZF1. So this part we have calculated. Now this will come in series with this 1 millihenry inductance, and the series combination of this with this inductance will give us final ZF. So for final ZF, I can write this value plus inductance in Laplace domain, so that will be replaced with SL. S will be S and L would be basically 1 millihenry, so 10 to the power minus 3. So this is the ZF. I can solve this further and I will get 200 plus this will get multiplied here, so I will get 0.2 S square into 10 to the power minus 3 plus S into 10 to the power minus 3 divided by 0.2 S plus 1. So this is what I will get here. Now this is ZF, and if I have to find V out upon V in, so I need to do minus of ZF upon Z in. So if I put this value and divide with this one, so the final value which I will get here would be equal to, or maybe I can put it here to show you how we are solving this. So this value I will divide by Z in. So if I divide this value with Z in, 0.2s plus 1 into s into 10 to the power minus 3. So this will get multiplied with this numerator part, and these two will become whole square, obviously with minus sign here because this is inverting opamp. So the final value which we will get here will be equal to minus 2 into 10 to the power minus 7 s cube plus 10 to the power minus 6 s square plus 0.2s divided by 0.2s plus 1 to the whole square. So this would be the final value. Obviously this minus sign will be for applicable for all, so this will be under bracket. So this is the final V out upon V in Laplace domain. So this is the transfer function of this given circuit. So I mean, from calculation point of view, it's all about mathematical, but what was important here is to how you are replacing this, how you are calculating the input impedance and this feedback impedance, and you must be knowing the concept of this inverting opamp. For inverting opamp, transfer function is basically equal to minus feedback impedance divided by input impedance. So other than that, it's all about calculation only. So thank you so much for watching this video. If you found this video useful, please like this and share with your friends. And if you haven't subscribed our channel, please do subscribe.